Let me start. Hello, welcome everybody. Welcome everybody. Ooh, with all the beautiful technology. Yeah, nice. So today I'm going to talk about gossip, which is a very different kind of algorithm than what we saw before. Let me explain first. Before, up to now, we looked at small systems, but now we're going to look at large systems. So in small systems, the number of nodes is small and known. Known, small number of nodes. And failures happen, but they are kind of rare. We don't expect them to happen all the time, but just once in a while. Okay. In large systems, we have an unknown number, a very large number of nodes. For example, a social network, how many people are connected to Facebook at any time? Who knows? Even Facebook does not know, okay? Failures are common. They happen all the time. They are normal. People don't realize when they are building small systems that failures are the normal case, okay? In large systems, we really see that failures are happening all the time, and the number of nodes is so big, and they're so spread out, that we don't know how many there are. There could be millions, or 100,000, or 10 more, less, or more. It's always fluctuating, so a very large number of nodes, and the number is unknown. Even finding out how many there are is very hard. Whereas in small systems, we know there are n nodes. N is some small number. Like here we have like a distributed database, Cassandra, MongoDB, whatever, with a small number of replicas which is known. 5 maybe, 5 replicas, or 10 replicas, or 32 for a very big one. But here we can have hundreds of thousands of nodes talking to each other and doing something together. The algorithms in this area are known as gossip. There's also peer-to-peer algorithms. There's also what's called content dissemination algorithms. There are all kinds of very large diffusion, whatever. There's algorithms that are made to work for very large unknown number of nodes. So that's the second part of the course, and so the next lectures will be on that. And today we're going to talk about one of the most important ones, which is gossip, which is used a lot actually. Even when people don't know it, they use it. We're going to talk about gossip algorithms, and you can do many things. Information dissemination. I'll talk about small world networks. This is a very important property of social networks, and it helps a lot, the gossip. I'll talk about a gossip framework. This is basically the code, a generic gossip algorithm. The algorithm is very generic. You can plug in what you want, and we can do many things. I'll show you how to do aggregate, things like broadcast, or finding some average property. What is the average percentage of the CPU used by all the people connected on Facebook right now? That's hard to find out, but we could find it out. And well, how many people are connected? That's hard, but we can find it out. Also, topology management. Maybe we want to take a messy thing and make it nice. Maybe we want to take a bunch of nodes that are kind of unordered with neighbors talking randomly, and we want to make it so it looks very beautiful, like a square or a ring or something very nice, okay? That's called topology management. Also, heartbeats, how big systems can start behaving, synchronizing. The example here is fireflies in a tree. In some countries where you have fireflies, lucioles in French, they flash lights, and sometimes they get synchronized. How does that happen? Well, that's a kind of gossip, because each firefly only sees its neighbors, okay? That's a gossip algorithm. And those are the things I'm going to explain. So I'm going to start by giving you some kind of introduction. Gossip is very intuitive, okay? Gossip algorithms, they're also called epidemic algorithms because diseases, they kind of spread like that too. People get in touch with random other people and the disease spreads. So in very large dynamic systems, so dynamic is another way of saying that the number of nodes is unknown and it's changing, okay? Gossip is scalable, works for very large systems. It's extremely simple. The code is actually simpler than the code we've seen before, than last week and before. And it's extremely robust. Even when messages get lost, when network breaks, when nodes fail, it's extremely robust. It's normal because, that's reasonable because failure is normal, okay? So that's gossip. That's a beautiful, it's nice, right? Looks nice, huh? But gossip is very intuitive. So I know something. I'm sitting next to Ali. So this is the same Ali we met before, Ali Gutsi, who is very famous now. But in these days, he was a student, and I tell him something, and we know. And he tells two other students, Cosmin and Talat, two other students. So it's like word of mouth, bouche à oreille in French. This is called a push academic, when people push the information, but you can also bring the information back. If I tell something to Ali, but he gives information back, and maybe asking something, then it's pull. So I'm asking for information. Or push-pull if information is going in both directions. So there's three kinds. There's the push kind, which is just dissemination. But pull means you want to gather information into one place. And push-pull means you want to do it in both directions. So basically you want to send something but get something back. Okay? So that's the idea. Okay? And notice that each node, each participant only does a small amount of work in this. So even if the network is huge, the participant load is constant. Okay? Each participant has a constant number of neighbors. Even if you have 1,000, 10,000, a million nodes, the participants are doing the same amount of work. And the total network load, so the total number of messages in the network, is linear in the system size. That's very reasonable. If I have 1,000 nodes, then I have 1,000 messages. If I have 1,000,000 nodes, I have 1,000,000 messages, okay? And if you look at what happens, the spreading is actually logarithmic. It's like a binary tree or something. If I tell 10 people something, and they tell 10 people, then in 2 steps we reach 100 people. So you can see the number of steps is logarithmic in the number of hops. But the network is not infinite. There's some maximum size, so you have kind of saturation effect. So you have this S curve, this typical S curve. You see it all the time. When the time goes up, and this is the percent of the system, I say it's infected. They have the information, okay? It starts by going exponential. So this is the exponential growth. But because the system has finite size, eventually it saturates. Eventually nodes start getting information from more than one neighbor. So the system reaches its limit and it saturates. This curve is called the logistic curve. It's a very famous curve. It's almost as famous as exponential curve or Gaussian curve. Many real-world systems are behaving like this. disease infection is one we'll see, you know, COVID behaving like this, but also things like animals. If you have rabbits and foxes, the amount of rabbits will increase until the resources of the system is reaching its limit, okay? So this could be number of rabbits. And if you have rabbits and foxes together, then it can do weird things like oscillate. But we're not going to look at that. We're going to look, this curve is really a basic curve, okay? There's, the algorithm is extremely generic. It's very simple. It's always the same protocol. It's a cyclic or periodic protocol. It happens kind of in waves, okay? It's a pairwise interaction between peers. A node talks to another node, and then it gets a response back. Now that's the, each peer is doing that. And the amount of information exchanged is bounded here. And the nodes have neighbors, so they have random neighbors, and they might pick a neighbor, okay? The state of each peer also is bounded, okay? So you can see it's very simple here, huh? And here also you have bounded state. So you send a small piece of information to the other peer, you send some information back, and you do a small computation. That's it. And every node does that over and over again. Yeah, question?
Like bounded states, you mean the number of different states?
No, I mean that the amount of memory in bytes is not infinite, it's finite. I mean there's a finite amount of memory here. Okay? It's a regular computer, and even if the network, the number of nodes is growing millions, or 100 millions, or a billion or more, like Zuckerberg, he loves to say that they have a billion in Facebook, then the amount of memory on each one node is still small. So it's bounded, that means there's a finite upper amount of memory. Okay? So that's how it works. It's very local. Each node is always doing the same thing. And then we're going to look at how the whole system behaves. Okay? So how does then the whole algorithm work? Okay, each node has to pick a neighbor. It has random neighbors. There is a random peer selection. So these are called peers. Huh? A node has its peers that are neighbors. There's different ways to do it. We're going to see different possibilities. Huh? Either it can pick any node, anywhere, full set of peers, millions, or maybe it has only a small set of neighbors and it picks one of its little neighbors. Okay. We don't assume the communication is reliable. Messages can get lost. We don't really care here. The cost of the protocol is negligible. That means the amount of computation done here is very, very small. Okay? So the message round trip times can be high, but it doesn't actually have to happen so often. Okay? The nodes don't have to communicate all the time. They can communicate and then they go to sleep. And a little bit later they communicate again. So it's very kind of vague and random thing. Okay. So how does that actually give reasonable algorithms? We're going to see. I'll give you some examples of how it works. And then we will look later at a real nice framework called T-Man. The framework, this was a famous one. The code is very simple, and it was used for some very sophisticated things. We'll see how it works. So the easiest gossip is information dissemination. So you're just sending, it's like broadcast, okay? You want to disseminate. And it's like a multicast, because you're only sending to maybe a subset of nodes. But it could be anybody. Event dissemination means that you are sending news, like events, things that happen. You're reporting events, okay? Or you can have background dissemination. This actually happens a lot. It means that your computers are always talking to each other a little bit. If you have a Windows machine, it's occasionally talking to Microsoft headquarters, and sending some information. Who knows what it's sending? So this is happening all the time, okay? These background protocols are actually very, very common. And because they have such a low load, you don't really notice them, okay? That's used a lot. Here's another use for gossip. Repairing, fixing things. This is something we didn't really talk about. What if the data on a disk is corrupted, okay? What if I have 2 copies of the disk and one of them gets corrupted for some reason, cosmic rays or something, right? It happens, the world is not perfect. This is known as anti-entropy protocol, and all big systems are doing this. You don't see it because it's happening in the background, but they're always doing a little bit of this. They are always saying, I have this information, is your information consistent with me? And if it's not, then they repair, okay? One of them might have more reliable information than the other one. The other one is corrupted or something. I have 6 updates from Cosmin, so one of the nodes has more information, more recent than the other one. Okay, so you can repair broken replicas, and many systems do this. In fact, almost all cloud databases are doing this. Okay, even though you don't know. If you're taking a cloud computing course, I don't even know if my colleague Ramin is talking about these protocols, because normally you don't really notice them, but they're always running, they're always in the background, okay? Anti-entropy. So the system is always kind of fixing itself. It's very biological, huh? It's like if I scratch myself, then the body repairs itself. Well, here it's kind of the same. Small problems will be fixed automatically using gossip. And this is always happening, okay? And you can even do more with gossip, which is the actual replication itself. If I have a database with 5 nodes, if 1 node crashes, then I only have 4 nodes. Well, what happens is I will reboot a 5th node, because I always need 5, and that 5th node I have to put data there. So one way is just to copy from another node, but another way is that replica will gossip and ask for the data. Ask the nodes, please send me this data, please. And eventually it fills up like that. And the advantage of this is that it's very low load, okay? If you immediately fill it up when you boot it, it overloads the network in a short time. But maybe you don't like that, and since it's very rare, you don't care if it takes a while. Gossip algorithms, sometimes they can be slow. They're very reliable, but they might be slow. But sometimes you don't care. So the replica will fill up with gossip data. And here's a third typical use, is you have algorithms that have 2 parts. You have a small part, like what we saw, the small, best effort, whatever. And then you have gossip to fill the gaps. What it means is that you use some very nice algorithm, very efficient, to send information, but maybe not everybody gets the information. Maybe not everybody is connected. Maybe a new node has just booted, it's not actually connected yet, or there's a failure, so the routing didn't go so well. There's some problems, okay? Doesn't matter, because after that, you will have a gossip will run, and we'll notice if there's a node with nothing. The node says, did you get this information? And the node replies, no. Oh, here it is. So the gossip fixes any small problems, okay? So this 2-way, this double use, bimodal modcast it's called. Bimodal because you have two main algorithms there. This is used a lot. You have a regular algorithm that works most of the time, and then you have a gossip algorithm that is slower, but it makes sure that everybody is reached. Okay? So you can see that gossip was already there in the first part of the course, even though I didn't talk about it. Okay? all large distributed systems are doing gossip. They're all doing it, even if you don't know. Okay. Membership. Let's say you have a large group of people, and they're members of some association, whatever, some club or something, or it's file sharing, BitTorrent. Some of them have copies of the files. You want to know who. So who is the members? Who are members? I don't know, because new nodes are always coming. They become members, but maybe they leave, or they crash, or maybe they just turn off their computer and they're not member anymore. So how do you know who's members in this group? You use gossip. It starts with what's called a bootstrap. So a few nodes that are stable, where they have been members for a long time, they're listed on a website, okay? Like maybe you have 20 nodes on the website. Like for BitTorrent, you have these entry points. You just pick one. And then you talk to that one, and you ask questions. Like, who have you heard about? So it tells you, here are the processes I've heard. So this is like an entry point. Maybe I have thousands of nodes, but I only know 20. But I want to know who has the file. Maybe thousands of copies of it, if I'm using BitTorrent, or something based on BitTorrent. Maybe there's thousands, but I don't know, and they're always changing, so there's no way you can store it. It's always changing. But there's a few that are going to be stable, or maybe somebody actually especially makes one of these stable ones just to make sure that there's a way of getting into the system. And then these processes do gossip, bouche à oreille. They say, this is the process I've heard about. And I've heard that somebody heard, etc. So the information is propagated. Okay? Or when you join the system, you can use push gossip. It says, I'm joining the system, I tell everybody. That's push. I'm now in there, and I'm telling everybody, and they propagate. So many people know that you're in the system. And when you want to connect, you know that one is there. So you can do both pull and push. So you can see membership, where things are changing a lot, is done using gossip. Okay, so this is not like any algorithm we saw in the beginning of the course. It's a quite different kind of algorithm, because there's no real guarantee, but it's extremely robust. And maybe it's going to be slower sometimes. There's more things. Here's one. Aggregates. Let's say I want to compute a property of the whole network. Like, what is the total computing power of everybody connected to Facebook? It's a lot, but how much is it? Okay. Or maybe you have something like SETI, which is Search for Extraterrestrial Intelligence, where you have SETI at home. I don't know if you've heard of this. They have to do a lot of computation to figure out whether the signals coming that they hear from the stars are intelligent or not. Okay? You have to do kind of pattern matching, and they don't have enough computing. So they ask for volunteers, and you can volunteer. I'm not sure it still existed. It used to be very popular. And you can connect to this, and they will give you tasks, and you will run it and give the answers. So that means these guys have a huge computing power. They could have thousands of people, volunteers like you, helping them. And people like that because they're part of the project. But how much is it? How much computing power? That you can compute that, but you need gossip. Because the number of nodes is always changing. People are connecting, disconnecting all the time. So this is called an aggregate. It's a property of the whole network. Some function of the whole network. How do you do that? Well, the gossip can do that. It will sample the information at all the nodes, and it will combine the values, like, for example, adding them up, or finding an average. You have things called wave algorithms, because the information is kind of propagating out and then coming back. Average, maximum, minimum. So what is the average time that people connect to Facebook? Total average. Or what is the average time that people do connect to SETI at home? Who knows? But you can make a gossip algorithm to compute that. Okay? And it's gossip because the number of nodes is large and unknown and there's always failures. That's a typical way of doing gossip. So you see, it's nice, huh? The gossip. So you see, it's a very different approach from what we saw in the beginning of the course. So this is the other side of distributed systems. And it's like a coin. There's two kinds of distributed systems, the small and the large. And they're both important. Large are like social networks, but small is like many systems are like this, like a bank or cloud analytics or distributed databases. They're small. But then the people connected together, it's large. So you have both. Here's another kind of protocol. This is called network topology. Protocols that arrange network topology. That's already something more complicated. For example, a ring. Let's say I have 1,000 nodes and want to connect them into a ring. That means each node knows one neighbor which is close by, and that node knows a neighbor which is close by, and so on until you have one long ring. If I just give you 1,000 random nodes, how do you make a ring? I don't know, it's hard, okay? T-man is the algorithm we're going to see. It's able to do that. It's a gossip algorithm that will construct topologies like rings or cubes or torus or whatever topology, okay? And how does it work? It's like a convergence. Each node has a view, okay? So that means each node has a few neighbors, but maybe they're not the right ones. If you want to do a ring, I need to know a node which is close by and on the ring. Maybe I don't know that one. So I start with some view, but it might be completely wrong. And now I exchange the view with the view of a random peer. So the node picks another node randomly, and they basically combine their information. That one also has a view. This one has a view, and that one has a view. So that gives me twice as much information. But out of this double information, I can pick all the nodes that are closest to me. So this is actually better than my original view. So I have one view. This is a node, but here's another view. So this gives me double information. And now I pick the best ones out of this. This gives me again one view. So basically I go from one view to one view by bringing in the information from another node. So here I pick the best out of double. So if there's 100 nodes, 100 pieces of information, here's 100, I have 200 here, I pick the best 100. So the second view is going to be better than the first one. It's going to have nodes that are closer to what they should be in the topology, you see? So it's like a step in the right direction, okay? So this is like a convergent algorithm. You get the intuition, how it's working? It's not an easy process, but each time you look at a node, you can improve your view. And then you keep doing it, and you pick another random node, and after a certain number of iterations, you will have a perfect ring. Actually, that's extremely efficient. They made, the two guys who invented T-man, they made all kinds of experiments, and it turns with a very small number of iterations, it's done. So it's actually a very efficient way of building topologies, okay? So that's another one. Here's, so this one we're going to see also a little bit later. Here's another one called hybrid gossip. This is an example of the two-layer approach, okay? Here is a broadcast algorithm using a spanning tree. A spanning tree is basically a tree that connects all nodes together. So there's only one path between every two nodes. This is the most efficient if you want to do routing for broadcast. If you want to do a best effort, which is extremely efficient, you construct a spanning tree, okay? So it's efficient. This is the most efficient you can get, but it's fragile. If one of these connections breaks, then you lose a lot, okay? Then some nodes get nothing. Or if one node crashes, some nodes get nothing. So this one is efficient but fragile. And then you combine it with another algorithm, which is resilient, so opposite of fragile, but slow. Now that's the gossip. So you have an algorithm out of two parts. There's a spanning tree, and then there's a gossip part. And if any node does not get the information in the spanning tree, it will get it through the gossip. Okay? And if the failures are kind of rare, this is very efficient. It's both efficient and resilient. So this is kind of a sweet spot. This is a really good way of combining a regular algorithm, like this one is like best effort implemented with efficient routing. That's this one. But it's fragile. Doesn't handle crashes. Oh. So one way to fix that is to add gossip. Okay. This is actually a famous algorithm called Plum Tree, which is implemented on many cloud databases. So the React database, for example, which is one of the big cloud databases, if there's a problem connecting the replicas of the database, it uses this algorithm to fix that, to find a connection. And sometimes you can have 50 or 80 or 100 nodes on this database, a very big database. Sometimes you have problems. Notice that cloud machines are not very reliable. That's on purpose. Cloud machines are not very reliable. They're sitting in a data center, they're very hot, and they're kind of no-name Taiwan or South Korea machines, very cheap, so they crash all the time. Why do they do like that? Because it's much cheaper. And it's so easy. They just crash, and when enough of them are crashed, the database is built in modules, okay? Each module has like 2,000 machines in there, and if there's too many crashed nodes in there, they just take the module out and put in a new module. That's how companies like Google make very cheap data centers, So the machines can crash. That means the algorithms have to be very crash resistant for a database. So this is a typical algorithm that's used for that. Okay, so you can see gossip is used. There's many other things. Clock synchronization. If I have clocks running on different machines and I need to synchronize them, gossip is natural. Global failure detection. I don't have perfect failure detectors. Remember, perfect failure detectors are very hard. But with gossip, you can make the eventually perfect failure detectors, you can make them very good so they don't make so many mistakes. Because the gossip, all the nodes are talking to each other. And so if there's one node that may be crashed, if all the nodes agree that there's a problem with this one, probably there's a problem. Where if one node thinks it's crashed, maybe it's not. So with the gossip, we can actually improve the failure detectors. Okay? So this kind of thing. Also reputations. This is for things like security, if you have a good reputation. Okay, so that's kind of introduction. Okay, now I want to talk about dissemination. So now I'm going to talk about diseases and epidemics. Okay, how information propagates in gossip. And the way it works, I have a node, a peer, wants to disseminate. It has a buffer here. It sends to a certain number of other neighbors. Okay, and it says it forwards a certain number of hops. Okay, so there's a number of hops, t, time steps, and each step it forwards to f randomly selected processes. So they are randomly selected. They might not be random, but we'll start by making them random, and then after that I'll explain a little bit what happens when they're not random. Okay. So this thing depends on three numbers, B, T, and F. How many messages can you store in one node? What is the fan out? And how many hops, okay? And the property depends on those three parameters, okay? So we're gonna look at some cases. This is like disease epidemics. Given a system size n, so there's actually a fourth number, the number of population. So there's B, T, F, and N. So the size of one node, the number of hops, T, the fan out, and the size of the system. So that is determining everything. And information is propagating there. How long does it take to infect everybody? So that everybody gets the information. I assume it's a disease. I'm saying it's an infection, okay? This is a very relevant topic now. Does it depend on n? What happens when n gets very big? Does it take longer? Cycles. So a cycle is a single round trip done by every peer. They can all do it at the same time, huh? So it might be, it's a short time, a cycle, huh? Maybe it's 10 milliseconds or something. It's a single round trip done, but every peer does it, but they all do it at the same time. That's one cycle, okay? So that's a lot of processing power, huh? If I have 1 million nodes, they're going to do 1 million round trips in every 10 milliseconds, okay? So this now is actually been studied a long time ago. Here's a book, The Mathematical Theory of Infectious Diseases and Its Applications, from 1975. So this was all studied. I'm going to show you some diseases, and you can imagine which of these are applicable for COVID, okay? Here is a model called Infect Forever. I have n people, I have one infectious individual, and the idea is that if I am infected, I stay infectious. That means that when I have the disease, I keep spreading it. That's why it's called Infect Forever, huh? And YR is the fraction of individuals infected at round R. So round is like a cycle, huh? Round 1 means all nodes have done one round trip. Round 2 means every node has run 2, and so on, huh? In each round, every infectious individual tries to contaminate F other members. And then, from this book, which you can get, The Mathematical Theory of Infectious Diseases, we can compute what is the fraction of individuals infected at round R. And it's this function, 1 over 1 plus n times e to the minus fr. F is the fan out, n is the total number of nodes. So notice if R is 0, then this is 1. It's 1 over n plus 1. So this is like, in the beginning, there's one node that's infected. But then after round 1, okay, you have some number here. Okay, but this number decreases. So e to the minus fr goes down very fast, exponential decay, which you know, huh? So after a few rounds, this number gets very small, and this thing goes to 1, huh? Okay? Every round by a factor of e to the f. That's something you can prove. That means if I build a gossip, yeah? Question?
Do we consider that every node does his cycle at the same time? So
Yes. Well, they don't have to actually do it exactly at the same time. They're always doing it, okay? And because gossip is so resilient, they don't have to do it at the same time. So it's kind of hard to say this is the exact beginning of a round and this is the end. Okay, you can say now we're kind of after 50 milliseconds, we're sort of 5 rounds. But we're not completely sure exactly.
It's local information.
But no, it's not local because each round trip is the same for every node. So globally, let's say it takes 10 milliseconds. That means after 10 milliseconds, every node can do 1 round trip. Every node. And we call that 1 round. It's not very precise notion because they don't all start at the same time. They're not synchronizing, and the times might vary a little bit. But it doesn't matter actually. Okay? Doesn't really matter, especially it's exponential. So if you make a mistake by 1 round, It's not so important, okay? So the round is kind of a vague notion, huh? You can't really define it super precisely. But it doesn't really matter, okay? You can define it approximately. You can say if this is 10 milliseconds, then after 50 milliseconds, you can say it's 5 rounds, okay? It's a time, in fact. And you can make that computation, okay? You can compute the latency. So the number of rounds necessary to infect the whole system, it's in fact going to be logarithm, huh? So it's logarithm base f plus 1 of n plus a small, another log n term, okay? So the number of rounds is very small, even for very big systems. If you have 1 million systems and the fan out is 10, then it's 1 million to the log base 11, okay? So it's like 10 rounds or less, huh? So infection goes very fast, huh? We see with COVID, huh? Infection goes very fast. And it's even worse than you think. When I talk about small world network, you're going to see infection goes even faster. This is for random network, okay? Here, each node picks randomly, but if you do a network which is the realistic network, not random, which is called small world, which I'll explain in a little while, it actually is going to go even faster, okay? So this is even a worst case. This is for a random network, okay? So that's infect forever, but maybe COVID is not like that. Maybe COVID is like this. This is another model called Infect and Die. So each process communicates the message, but it only does that once, one round, and the next round it forgets things. So it forgets the message, whereas in the previous one it keeps sending every round, infect forever. Here it's only doing the first round. So it's like a diseased person. Let's say one round is like 1 week for the contagion. I get the disease, COVID or whatever, or bubonic plague or something, or tuberculosis. They were big, important diseases a long time ago. COVID is still important now, but maybe in a few years we forget it, okay? And once I get cured, I'm not contagious anymore. I don't pass it on. So it's like this model, okay? I'm only infectious for a short time, for 1 round. So this is called Infect and Die model, and again you can compute the total number percentage of the population, okay? This one is actually much more interesting, because it's not going to converge to 1. If it can actually die out if you do it for the right cases. If I don't contaminate anyone, 1 week later, it's over. There will be no more, okay? But if I contaminate people, but then the ones that contaminate will eventually no longer contaminate, okay? And so this is actually a fixed point equation. So we'll say pi is the number of processes which are eventually contaminated in a steady state, okay? And it satisfies this equation. So you have 1 minus e to the minus pi f, but that's equal to pi. So basically, at some point you have some kind of a stable situation, yeah?
So when we say infect and die, so if you have a node that is infected, then it dies, but it fades?
Actually, in this case, that's a good question. In this case, it remains infectious around round, okay? But then it will do, even if copies of the same messages are received again, it will do nothing. You might have, that means once I get cured of COVID, I will never get it again. But some diseases are not like this. Some diseases I might get it again, and then you have even different equation. In this one, eventually, everybody becomes, so the number of processes contaminated is not going to be 1, because eventually it dies out. Eventually, the fan out is only touching people who were already cured, you see, because of the fixed size. So maybe I have 100,000 out of 1 million that are cured, and there's still 10,000 that are infected, but by accident those 10,000 are going to talk only to the 100,000, it dies out. So eventually it's going to die out, huh? But if you pick them randomly, you can do like an average case. That means eventually it will die out, and the number of processes that get contaminated will be some fixed number, and there will be nobody more. See how it works? So this is kind of like, well, unless you have new variants of COVID, this is kind of like COVID. Huh? New variants makes it that's more like the previous one. Huh? If you have new variants coming all the time, like they had this Delta variant, and now they have this Omicron variant, eventually they run out of Greek letters, and we're good, right? So nobody knows how infectious Omicron is. Okay. But so all the epidemiologists, they're all doing these computations right now. They're all trying to figure out what's going on. Okay. In this model, you can see this equation is actually very interesting. If f is equal to 1, the fan out is 1, that means I will only contaminate one other person. That means only, eventually, that person, nobody, eventually I will pick a person who's already, and then it's done, okay? In fact, pi will be equal to 0, okay? In general, for a very big n, nobody, the percentage will be very small, 0, okay? When f is 1, when I'm only giving it to one person. But if I give it to more than 1, then there's actually a fixed point. So the value of 1 is like a critical value. If it's less than 1, it dies out immediately, okay? More than 1, it actually reaches some stable thing, but exactly equal to 1, it'll be 0, okay? And if the fan out gets very, very high, it will approach 1. So you can see it's kind of interesting, huh? This infect and die model. And you can actually model it like a dynamic system, okay? So here I have some equations. Here, this equation here is 1 minus e to the minus pi f. So this is when f is equal to 1. When f is bigger than 1, it goes higher, okay? And then the other one is x is basically this value equal to pi, okay? So that means the fixed point is going to be the intersection of these two. And you could actually consider a kind of iterative process. I'm not going to handle that here. I think actually there's courses in applied mathematics where they treat these kind of dynamic systems. Huh? This is a very nice kind of dynamic system. But you can see that this equilibrium here, it's either stable or unstable. But in this case, it's going to be stable equilibrium. And you can see as f increases, then it gets closer and closer to 1. Huh? If f is equal to 1, it's 0. But then it increases, and as f gets bigger, it reaches 1. Okay? So the fan out is very important. If I have low fan out, almost nobody is going to get infected. That's why they like to break the connections for the COVID. If you have what's called the bulle, your bubbles, the people that you talk to, and the two bubbles are not talking to each other, then the fan out is limited, the size of the system is only in there, and the fan out is limited, then you will actually be lower. Huh? So you can compute all that, and the epidemiologists, they love computing it. Huh? So this is an interesting one. So with this you can compute the behavior of gossip. This is the case when your nodes have limited memory and cannot store. Okay. In gossip it's not as life-threatening as a human disease. Huh? You could also compute the latency. Okay. The number of rounds. So f, if you want to reach the whole system approximately, if you want it, then f has to be big enough. It actually has to be some proportion to the logarithm of n. If you don't have enough fan out, you will only reach a small number of people. If you reach that, then you will reach almost everybody. And then the number of rounds will be log n divided by log n. Okay. So this is pretty much the same as log n. Log n, it's pretty much like a constant. It's growing very slowly. It's interesting, isn't it? And it has real-world applications even. So the gossip algorithm is actually the way real-world life is working. And now you can do all kinds of stuff. So I'm not going to say much about that. Now, of course, you can tweak many things in gossip. Membership. How do the peers get to know each other? Okay, I assume they're picking random or neighbors. How do they do that? And you can do a trade-off. If I only know a small number of them, then maybe if it's the wrong ones, the network gets disconnected. You see, I'm less reliable. Maybe if I only know a small number of neighbors, and if it's not the right ones, then I will miss part of the network, you see? So there's a trade-off, scalability and reliability. Okay? And then there's other things I'm not going to say so much. Network awareness. So that means connections that are close to each other in the real world should be neighbors. If all my neighbors are in Japan, I'm going to have slow gossip. But if my neighbors are all in Louvain, I will have a fast gossip. So this is called network awareness. And then the topology, the buffer management. When the buffer is full, who do you kick out? Okay, who do you throw out? Okay. So let me see. Maybe I'm not going to say. Let's see. Is anything interesting? Every process will only see some of the other nodes. Okay. And if you really want it to work, it has to be a random sample. That means it has to be as if I've picked them randomly, even when you have churn. So churn is an important concept, which I define here. Churn, it's like making butter. You're mixing. So the churn means that the set of nodes is changing, but the size of the set is constant. That means you have a churn when you have 1,000,000 nodes, but the identities of the nodes are changing. So maybe every hour there's 1% different nodes. So the unit is some percentage in terms of time. Okay. Every hour, 1% of the nodes will change. So that's a churn value. But there's always 1,000,000 nodes. It's just that the identity, some of them are always leaving and new ones are replacing them. That's the idea. You have failures, it's normal, but you also have new nodes coming in all the time. So somehow the total number is constant. So we're assuming some kind of a steady state. The total number is constant, but still there's nodes failing. So there's a property of that which is called churn. You can for some gossip algorithms, you can figure out what it does in terms of churn. Okay. Okay. Let me see if I want to say. Okay. This is all blah blah. I'm not going to say anything here. Okay. Let me skip the blah blah slides and go to all the interesting ones. So this is now I'll say something about small world networks. And what it basically means is that the real gossip is going to work better than you think, or worse, depending on what your notion of good and bad is. But let me make a break now, and after the break, I'll talk about small world. On internet or in the real world are actually this kind of network. And when this was discovered, this was a major discovery, that this is a very special kind of network. Let me explain. So the question, how do infected process choose the one they infect, their targets? So it depends on who they are connected to. Who is their friends or neighbors? And we talk about two kinds of networks. Nearest neighbor, so I only know neighbors that are close by. So I have a small set of close by neighbors, and each of those guys has also some small collection, close by nodes. So the processes will only have local neighbors, and this is called a nearest neighbor network. There's only connections that are like physically close to each other. Okay? And the opposite kind of network is called a random network, where if I have n nodes, I pick randomly any one of those n. Whereas in the nearest neighbor, I have a small number of neighbors and they have neighbors. So it's like there's like a path. If I want to go far away, I have to go through many links, okay? So these are two kind of logical structures, right? Nearest neighbor, it's like everybody only has a few friends, and they have a few friends, and so on, and it goes over the whole world. Or random, it means you can talk to anyone. You can pick up your phone, dial a number, and talk to anyone in the world. That's a random network, okay? But real-world networks are different. They're not nearest neighbor, and they're not random. They're something that's kind of in between. And this is the small world network. And let me explain what it means. So there's very precise, this is very precise thing, a small world network. And it's not random, but it's also not nearest neighbor. And I will give you a definition, but first I want to say that all, I say most here, but in fact all real world networks, all networks coming from people, are going to be small world networks. They are going to be this kind of network. And not random, and not nearest neighbor. So people, when they know other people, it's not random. You don't know randomly a selection of people across the world, but you also don't only know your neighbors. It's something in between, okay? This is actually, there's a course, if you're interested to understand more, which really goes into that and see what it means. Reasoning about a highly connected world. So this course really goes into internet structures, okay? But today I want to tell you what is a small world network, because it really affects gossip and other things, It affects many things, but especially gossip algorithms. They tend to converge faster than they would with other kinds of networks. The small world is really good for that, okay? Let me give you some intuition. A small world network, it has nearest neighbor connections, but it also has far away connections. It has both. But it's not one or the other. A random network would basically only have far away. If I pick a random node over the Earth, the chance that it's going to be in Louvain is very small, okay? They're going to be all very far away. Whereas nearest neighbor, they're going to be all close. But a small world network has both close and long connections. And it turns out all networks coming from people are small world. For example, your friends. Think of the people you know, each one of you. Who are your friends? Some of them are close by. Some of them are in Belgium. Some of them might be in foreign countries, right? So who of you has a friend who's not in Belgium right now? So raise your hand. That's a lot, okay? So you have long-range connections. Those people are far away, okay? You maybe even have family in foreign countries, okay? So I have some cousins who are living in the United States, for example. Or I have a friend who is friends who are all over Europe, everywhere. But also I have friends here, okay? So you have both nearest neighbor and long range. So that's kind of an intuition. But you can make a formal definition. A formal definition, there's two properties. Small average shortest path length and high clustering coefficient. So what does it mean? The small average shortest path length means that between you and anybody else, there's a short path. You probably have heard of the 6 degrees of freedom or something. I'll mention it in a few minutes. That between you and anybody there in the world, there's a very short path, okay? Very short. And of course you have to find it, but between you and even somebody in some random village in Tajikistan, there's going to be a short path, okay? That's a property. In a nearest neighbor network, the path length is long, of course. To go from here to the south of France, you have to go through lots of neighborhoods, 1,000 kilometers. So the path will be long. But in a small world, it's short. Between you and anybody, the path is short. That's the first property. The second one is the clustering, that there's groups. A clustering means that the neighbors know each other, that they're like compact, okay? You can actually find that. So a random graph, where you just pick connections between nodes totally at random, from one node to any random other node, it has low clustering. It's very spread out, okay? It's very spread out. Whereas a neighbor graph are very clustered, but of course they have long paths. So in a neighbor graph, everybody in the village knows each other, so they're very clustered. But if you want to go to southern France, it's a very long path. Whereas in a random graph, everybody in the village doesn't know anyone else in the village. They only know people who are 1,000 kilometers away. That means the path length is going to, the random path is not going to be clustered, okay? But you will be able to find usually a short path, but it will be very diffuse, okay? So I can define the path length, the shortest path length between you and somebody else is the number of links in the shortest chain of friends between you and that other person. Over the whole, everyone on Earth, that's the shortest path length. You can define that. The clustering coefficient, intuitively it's how compact it is, it's clustered, but you can define it, okay? For a node, you count the number of edges between neighboring nodes. So let me make a picture and then you can understand what it means, clustering. Okay, so here I have a node, and it has neighbors, okay? Here's the neighbors. So here's node A, and then there's neighbors, B, C, D, E, F, G, okay? And that's an E. Clustering some of these neighbors, so these are my friends, these are friend connections. Some of these people, they know each other. Maybe G knows B, G knows E, G knows C, C knows E, and so on. So maybe some of these people are also friends. So the clustering coefficient measures how many of my friends are also friends among themselves. Okay? Okay? Count the number of edges between neighboring nodes. So that means the number of my friends who are also friends. So I'm a friend with B, and I'm a friend with C. But are B and C friends? If they are, we count them. Okay, so you take all my neighbors and you count that, and then there's a maximum, huh? If everybody is friend with everybody, the clustering coefficient is 1. But if nobody is, if it's just like a star, then the clustering coefficient is 0. Okay? So you know it's going to be somewhere in between, huh? But in a small village, in a very small village, it's going to be closer to this. Or in a family, huh? In a family where I have 6 brothers and sisters, of course they all know each other, huh? So you're more like this situation. Whereas people that randomly meet each other in the street, it's going to be like this. If I meet 3 people, they're not usually probably going to know each other, huh? So that's the clustering coefficient. So a random graph will have very low. It'll be more like this. Because the neighbors will be very far away, okay? This one is 1,000 kilometers away. It's a random node. This one is 150 kilometers away. So the chance that they know each other is going to be very low, okay? Because they're 850 kilometers at least from each other, okay? So the random graph is going to have low clustering. It's going to be very spread out. Whereas the neighbor graph is going to have a lot of clustering, okay? But of course the random graph is going to have shorter paths, but the neighbor graph will have long paths, okay? And you can make kind of a diagram. So here are 3 kind of artificial ways of seeing it, okay? So here I have nodes in a ring, and this is a nearest neighbor graph. So each of these nodes has 4 neighbors. You see this node has 1, 2, 3, 4. And it goes around. So this is a typical nearest neighbor graph. It's very regular, but it's kind of like this, where each node has neighbors. And you can see that this node is a friend of this one, but this node also is a friend of this one. So it's clustered. But if I want to go from one side to the other, it's very far, okay? I have to do a lot of steps. So I'll have a high path length, but also high clustering, okay? And here I have random graph. So each node will go to some random node across the whole thing, okay? Now it's very unclustered. This guy will have this one will be a friend, this one will be a friend, but these two are probably not friends, okay? Because they're far away. So it's lowly clustered. But it also has low path length, because you can find paths, even though they're weird. From here to here, there's a path which is like this, okay? The path might go back and forth, but it's there. So the small world is in between. It has both neighbor connections and far away connections. See, this is a far away connection, huh? But this is a neighbor connection. So it has kind of neighbor connections, but it also has these far away connections. So the nearest neighbor graph has long path length and high clustering. The random graph has low path length and low clustering, but small world is in between. It like takes something from each. It has the low path length of random and the high clustering of nearest neighbor. So it's like both nearest neighbor and random somehow. Right? It's combining both. Okay? That's kind of that's the formal definition. But there's a huge amount of intuition on this. This is called the 6 degrees of freedom problem. This is actually a famous sociological experiment done by a guy named Stanley Milgram in 1963. He forwarded letters. He said, I have a guy living in Boston, and I'm going to give a letter to somebody in California. So that's on the opposite side. And all I'm going to say is, just send that letter to somebody you know who you think is closer to Boston. Because they're not going to know the guy in Boston. So the guy in California sends a letter, and it goes a little bit. And then that person has to do the same thing. So eventually, the letter will find its way to the guy in Boston. You see how it works, huh? How many steps? Well, here is the number of intermediaries and how many chains, okay? You can see that the high point here is 6, okay? So, and in fact, the median path length, the one where you have the same number of less and higher, is 6. That's very small, isn't it? That means you only have 6 steps between 2 random people far away from each other. You can find from one to the other in 6 steps. And you can actually find it. If you send it in the good direction, it actually gets there, okay? The median path length is 6. And this is where the famous thing about 6 degrees of freedom comes, huh? And this is true in many different situations. You can actually find databases. There is something called the Bacon number. Have you ever heard of that? Anybody? There's an actor called Kevin Bacon. Maybe you heard of this guy? No? Actually, he's played in a lot of movies. And the Bacon number is, it's 0 if you play in the same film as Kevin Bacon, but it's 1 if you play in a film where there's another actor who played with Kevin Bacon. You see? It's how many films you have to go to get to Kevin Bacon. So all the people who played in the same movie as Kevin Bacon have 0 Bacon number, and the ones who played in the movie with somebody who did play with Kevin Bacon have 1, and so on, 2, 3, so on. Most actors have very small Bacon numbers, like 3 or 4. There's actually some people try to find very large number. So there's like some obscure movie filmed in a small village in the 1920s in the Soviet Union has somebody with Bacon number of 7, okay? Something like that. So you can see it's usually very small, okay, this Bacon number. And the same for scientific papers. Something more interesting for me. There's a very famous mathematician called Erdős. I forget his first name. Paul Erdős. He's a Hungarian guy. But the guy, he's very weird. I mean, he's dead now, but he was very weird. He didn't have any fixed address. He would go to some mathematician's house, stay there, write a paper with that mathematician, and eventually get kicked out. And then he would go to another mathematician's house and do the same. And he spent his whole life doing that. So the guy wrote like thousands of scientific papers. He's very famous. So you can define an Erdős number, okay? And if you write a paper with Erdős, you have a number of 0. That's great. But so mathematicians, they consider having a low Erdős number to be very prestigious, okay? And there's a database where you can look up to see how is your Erdős number. And I know for a fact that our esteemed director, Vincent Blondel, he's very proud because he has very low Erdős number. Okay. It's actually, I think it's even 2 or something like that. It's very low. So the closer you are to Erdős, the better it is, supposedly. But that's part of this, you see. People you shake hands with. How close are you to Joe Biden, for example? Closer than you think. I can tell you why. When I was a student, I knew somebody in the dormitory. That person was actually a rabbi, and in his synagogue, at some point Joe Biden came. Joe Biden is Catholic, but he came because there was somebody he knew there. And so that means I'm connected to this guy, whose name is Michael, who's connected to Joe. So if you shake hands with me, you are only three away from Joe Biden. Yeah. This is completely true. When I found out this guy was Michael, I won't tell you his last name, but he's a very nice guy. He was in the same dormitory, we knew each other, and actually he was had a synagogue in Delaware, and Joe Biden is from Delaware, and at some point, Joe Biden, because there was somebody he knew who was there, a little old lady who was always giving him money, so he was very thankful. So somehow he went to the synagogue, even though he's Catholic, and he met this rabbi, and so they talked and so on. So there you go. So the far connections. So this is a small world network. You see, real networks are like this. And this really helps gossip, because it means you have all these long-away connections, these far-away connections. That means every network will have far-away connections if it's coming from people, okay? This is a network coming from human beings, because anything that is connected to the real world will be like that. It's weird, huh? So here's a picture of a small world network. So this is a social network, some snapshot of a social network. And you can see, it's hard to see, but there's links. There's far-away links, but there's also short links. There's clustering, but there's also far-away links, okay? So it's going to be a network with clusters, but also far-away links, okay? All real-world networks are like that, okay? And this really helps gossip algorithms, but it has an enormous effect on many things, this notion of a small world network, okay? Okay, so that's something I want to talk to you about. Now I want to talk to you about going really gossip, making gossip into a powerful tool. This is a famous gossip framework. So a framework is basically a piece of software where you just instantiate, you plug it in and it can do anything. Huh? This is Gelasity and Baboglu, who are two well-known researchers in networking. They made this framework. I mean, they're not the only ones, but this is one of the very nice ones. This is how it works, and you can write your own gossip algorithm. Each node runs 2 threads, an active and a passive threads, and both of them are going infinite loop, okay? The active thread, you wait t time units, whatever it is, so you have some time in between the round trip. It's not like doing too much, huh? So the load on the network is very low. You pick a peer, select a peer, you push your local state S, so you send it to Q, you receive the state from Q, and then you update your local state. That's very simple. Huh? You send information, you get it back, and you update your local state. And the passive thread, which is on the other side, it's always waiting. It does nothing, but it's waiting. Whenever someone says it, it will receive, push S to Q, it will receive those 2 values. It pushes its own state, S, back to the origin, and it also updates. So it's back and forth, and both of them are updating. This is it. All you have to do is fix find the two functions, select peer and update, and you can do any gossip algorithm. So this is how easy, see how easy it is, huh? So in order to instantiate the framework, you have to define what it means, the local state, the method select peer. Also, I show you push-pull, huh? But maybe you want to do only push or pull. So the code I show you is like the most general one, and you have to do the method update. This you can do any kind of gossip. Let me show you now some examples. Here's one. I start with simple, and I will end with a very sophisticated one, okay? Okay, I want to do aggregate. I want to estimate an aggregate. What do I do? So the local state is the current estimate. Maybe it's the average load of all the nodes on the system. The select peer will just pick a random neighbor. But notice this one, if you pick a neighbor, and if your network is small world, it will be as good as if it was a real random network, okay? Because you have these long range things. So the gossip, even though it's running with nearest neighbors, if you're using it on a social network, it will work as good as if it were true random, okay? Just an aside. Also, the update is some numerical function, like a mean, min, max, whatever, huh? You do some function and you keep going. So here is the behavior that you can see, the average. So some number, so each node has a number and you want to find what is the global average, okay? So the estimated average, these are the cycles. So each cycle is all nodes doing one round trip. Right? That's what I called rounds before. Huh? So you can see it starts very bad. Huh? But after 10, 15 cycles, it starts getting very good. Huh? It's very exponentially decaying. Huh? And if you look here, so this is 20. If you look here, here's like a zoom. Huh? 22, look, 1, 1.005. You can see it's really exponentially converging very fast. So after like 30 cycles, it's going to be like 4 digits precise. That's pretty good. And 30 cycles is not so long, okay? You see that? The convergence is exponential. You see how good it works, huh? The variance, so if the selected peer is a globally random sample, then the variance of the set decreases exponentially. Notice, it doesn't actually have to be globally random. As long as it's a small world, you're fine. That means you don't actually have to really do any work to make it globally random. If you're using a social network or something coming from a social network, it will already be like this. And the convergence factor will be, you can compute it. Huh? It basically, the zero, you improve the interval is multiplied by 0.3 at each level. So two cycles, and it's almost like 10 times better. Okay, that's one. Now let me give you a really interesting one, which is network size estimation. How many nodes are in the network? This is actually a really interesting question. Okay, I have n nodes, but how big is n? It's always changing. It's always fluctuating. Nodes are coming in, and it might be more in the evening when people come home from work. It might be less someday. So what's the idea? Here's an idea. If exactly one node has value 1, and all the others have value 0, then the global average will be 1 over n, of course, huh? Right? 1 divided by the number of nodes, 1 plus 0 plus 0 plus 0, etc. And then you just have to invert it, and you get n. Ta-da! That seems very simple, right? Now, the trick is, how do you make it work? So that's a simple idea. It's actually not that simple to make it really work, but we can make it really work. Okay? For example, how can we guarantee that exactly one node has value 1 and not more than one node? You tell me, how do we guarantee that?
Consensus?
Consensus. Oh, consensus on a million nodes that are always changing. It's not very practical, right? How do you implement that consensus? Or leader election, right? Oof, that's very hard. But you don't actually need to do that. You can be a little bit trickier than that. But yeah, but that's the whole point. We don't have a consensus algorithm that works on such system. Okay? So how do you do it? You have to be a little bit more smarter, a little bit more clever than that. I know there's very clever people in this room, but you have to be clever to do this, okay? This one is but once you get the idea, it actually works pretty well, okay? So how do you do it? Actually, you use some kind of trickery. So you don't, notice, you don't actually need linear election. Somehow I predicted people would say that. So how do you do that? Okay, how do you make sure there's only one node, value 1? Well, it's very hard. You use randomness. So you allow multiple nodes to randomly start the protocol. But it's a separate instance. So each node is like storing a vector, where each slot is like one instance of the protocol. And a node will, some chance, 1 out of 1,000 or whatever, 1 out of 10,000, it will start the protocol. And it'll be like the 1, and all the others will be 0. And how do we know the others are 0? Because we tag it with a unique identifier, some unique constant, randomly joined, selected, but unique. That means the one node that starts, all the other nodes, they will not have this identifier, so they will be 0 in the beginning, okay? So if you do that, then you can be pretty sure that each of your concurrent instances will have only one node that has value 1, and all have value 0, okay? Now you still can have a problem. You might have too many of them. Let's say you have 1 out of 1,000 is doing that, but if you have 1,000,000 nodes, you'll have 1,000 of them. Maybe that's too many. Well, you bound them. You say we'll have like maximum of 30 or something, or 50 or whatever, and you use some kind of a filtering technique. I erased it here, but similar to what I showed you before, where the node, when it talks to another node, it only picks out of the 200 maybe concurrent instances, it only lets 100 keep going. And you use a simple scheme that they're always going to be the same, like the maximum of the identifiers or something. So you have a scheme to bound the number of concurrent instances, so you don't have too many. Okay. And that will work. You can even make it work better. There's a trick that makes it work better. So if you do it like this, it actually might start wrong in some way. So you periodically restart the algorithm. So all of the current instances, once they converge, you stop them. And you use the median values from the previous epoch to start a new epoch, like a new generation, a new version of the protocol. Because the problem is it's too much influenced by assumptions you make here. What is this probability, for example, and by what is the real size? If the size is only 1,000, or if it's 1,000,000 or 10 million or 10 billion, then maybe the convergence will not be so good. So periodically you restart, use the median values from the concurrent instances, and you start again, and actually that improves the behavior. So you see, this simple idea is a good idea, you can make it work, but you have to do some things to make it work. You see that? So you have to be a little bit clever. So here's some experiments on that. Okay, the way it works now is I have around 100,000 nodes in this version. At the beginning of each cycle, 1,000 nodes are going to crash. Okay, and then 1,000 new nodes come in. So the churn will be 1% per cycle. Okay, and each of the dots here is a converged size from an instance of the protocol. Okay, so here you have the number of concurrent instances, okay, running. So if you have only a few of them, then it's going to be not very good. But if you have many of them, and then if you combine the information, it will give you better results, okay? So if you have many of these instances, like 40, it gives you pretty good estimates of between 95 and 100,000. Because how much is really the size, huh? After each cycle, 1,000 are crashing, a new 1,000 are coming in. So things are very much fluctuating, huh? So nodes, they don't live very long. And what's the average lifetime of a node? It's only going to be 100 cycles, huh? Here I don't know how many cycles it is. Each of these points is a converged value. So the axis here is not cycles, huh? It's how many of these concurrent instances we have running together, okay? So you need a certain number of them. If you have too few, then it's not going to work so well. So each of these is already converging after a certain number of cycles, okay? So this is a network very much in flux. Still works pretty good, huh? I mean, what is the real size? Here it tells you that it's going to be like 97,000, okay? Yeah, maybe it is, huh? That's one measurement. Here's another one where you have messages lost. Okay, here it's just regular gossip, except 20% of the messages are lost. 1 out of every 5 messages, poof, disappears. So that means the round trip doesn't work. For many instances doesn't work, huh? So, and then you would like time out or something, you have like failure, you can't do it in many cases. So a lot of the information gets lost. Again, look what happens when the number of aggregation instances increases. Again, it's pretty good. Here it's actually close to 100,000, but here actually the number of nodes is 100,000, it's not changing, huh? Not like in the previous one where you actually caused 1,000 to crash. Here it's only the messages that are disappearing, huh? So it works pretty good, huh? You can actually, but of course there's still some fluctuation, huh? Because yeah, these random messages lost will kind of mess up the computation, huh? Yeah?
Do we have a relation between the fluctuation that keeps on and the rate of crashes?
Yeah, probably you can compute that. I don't know what it would be. You can do some measurements, and this comes from the T-Man article, which is on the Moodle. So they have done some experiments, and they have done a little bit of analytics, but they haven't done everything. So there's many things I don't know on this, okay? Each of these dots, of course, is a converged instance, you have to remember, huh? So this could take already a number of cycles, huh? Each of these dots already takes a bunch of cycles, huh? To converge, okay? But it still works pretty well, right? What do you think of that network size estimation? That's actually a tricky thing to do, but you can do it with gossip. Totally through this gossip framework instantiating. Now let me go to something even more complicated. This is the most complicated one I'll show you, which is topology management. This is like the example I said in the beginning, where you want to create a structure. For example, I want to create a ring. I have random things with nodes with randomly networks. I have social network. Each person knows some other people. It's just totally like random small world network. But I want a ring or a square or a torus, like a donut structure from this, okay? This algorithm is called T-Man. It's in the paper. It does that. And it's a service. It's a general scheme. It can give you any topology you want, but you have to give it an input, which is something called a ranking function, which tells you how close you are compared to the topology, okay? And the paper talks about rings, toruses, which are like dinner tubes, binary trees, if I want a binary tree structure. This is actually used. Some of these databases, some of these systems, they actually need to determine topology. So when they start up, they do something like this to make a topology, okay? So this actually is a practical algorithm. It can jump start other protocols. Yeah, like I said, DHT, which is like the kind of peer-to-peer network, large distributed peer-to-peer structured overlay network, which is used in some big systems. You can jump. It's a big thing with the topology. So when you start it up, you have to get that topology, So this protocol can jumpstart it by creating the topology, okay? Now, how do you define that? Now, this is a little bit, there's some mathematical definition here. I have n nodes. Each node has some state, okay, which I call a view. And it has a size, c. So it's like a vector of c things. And it has information about other nodes. And it has the identity of the other node, the address, but it also has something called a profile. It has some information about how far away the other node is. It's a kind of distance, okay? But we'll see exactly what it is. And this, the input is a ranking function, okay? If I take a node x and I give it other nodes, okay, then it will order them in increasing distance. That means, for example, I'll give you, maybe I'll do an example because it's a little bit abstract. So I have other nodes, A, B, C, D, for example. It's the set of orderings, and each element is ordered in increasing distance. So it's a set, but they're ordered. So for example, B, A, C, because B is the closest, and I maybe have B, A, D, and so on. So it's like B, A, C, because B is the closest to X, so I have X, and then B is the closest, and then A, and then C. So somehow B is the closest, okay? Each element of R, so R is a set of orderings, so each ordering is ordered increasing distance from X. And there's some kind of distance function that we use for that. And this is related to this profile, and this will be kind of like distance function. And now, here's the problem. For every node, X, find the closest neighbors of X according to the ranking R. So if R, you can define R so it defines a ring. Okay? It's easy to define R so it defines a ring. Here's a ring, for example. Here I have X. Here's a ring, for example. A, B, C, D, E. So this would be a ring. Okay? So in this, the R of X, A, C, then A would be closer to X than C, okay? For example, A, C. Or E would be closer than D. Or E would be closer than C. So you can define, this R will kind of define a ring for you, okay? So each of the rankings kind of defines the topology. So you have to find the closest neighbors of X according to the ranking. So basically, what does it mean in terms of gossip? You construct a view. View is the state of X. View X, such that the ranking, that the R function contains a ranking that starts with view. That means view is the closest. That means X knows who its closest neighbors are. But in the beginning, X does not know that. In the beginning, X knows some random set of neighbors, but at the end, X has to know the closest ones. For example, A and E, or A, B, and E, D. It has to know that. But in the beginning, you have like a million nodes, and X doesn't know that at all. It just knows some random collection of nodes. Okay? So now we can instantiate the algorithm. So this is the framework from Chulacity and Babaoglu. Here's the active thread. Here is the passive thread. So we have the select peer function. We then have some buffer. Okay. So the view, the peer we select is somehow merged. So we have a view, but we'll just say buffer is like the local state. You send it to P. You receive view P. That's the state from the other one. So you have two pieces of information. you have a vector of size C here, which is buffer, and another one which comes from P. You merge these together, okay, and then you pick the ones that are the best. So if I make a picture of that, okay, I have here buffer, I have here view P. So these are like 100 element vectors, huh? Okay. I merge these two. So I have a merge here. And then I select view here, which is basically picking the 100 best ones. Here I have a 200 vector. Here again I have a 100 vector. Okay, so it starts from view. It goes to buffer. It gets the view from the other one. And then it goes to a new one. This is the new view. Okay, so basically I have my local information, which goes in the buffer. I pick the state from the other node. I merge them together, and I somehow pick the ones that are best. So the ones that are closest to me according to the ranking. And that's my new view, and then I repeat that. So it seems kind of straightforward, huh? You have random nodes, you get some other random nodes, and out of those double random nodes, you pick the ones that are best, okay? So you have to instantiate them. So the initial random sample merge is just union. Select is ranking the view according to R and return from the first half. So you pick the half that are best, okay, basically. You pick the best ones, okay, and that's it, okay? And you can define some ranking functions, okay? There's some ways you can define ranking functions. Here I define distances. I have a line. Let's say I want to make a line, which starts and stops. But a ring is like a line, but that connects, huh? So the line is just the absolute value of the difference, of the distance, of the position on the line. Here, the ring, I have two paths, huh? I can either go this way or I can go this way. So you have to pick the minimum of those two, huh, to get the ring. And from these two, you can define the ranking functions, okay? You need the ranking because somehow you need to find the 100 best ones, huh? Also, you can do mesh. A mesh is like a square where you have what's called Manhattan distance, where you go like this, basically, count the number of steps with boundary conditions. Torus is a square where you combine. Torus you see sometimes in games. If you have a square game field, when you go out on one side, you come in on the other side. When you go up, you come in on the other one. So that's a torus, which is like a donut. So this all gives you, these are all different kinds of topologies, or a binary tree. Binary tree, and you have a path. You go up the tree, go down the tree, okay? So you have binary strings giving the path on the tree. And the ranking, the distance is how many steps, okay? Up or down, and the shortest one is the one with the shortest steps, okay? So you can do stuff like that. It's explained in the paper. And here's some experimental results. So this is 2,500 nodes, starting from a uniform random topology. So the nodes are totally randomly connected. C is 20. That means each node keeps track of the 20 other nodes. Okay. A cycle is the time during which n updates happen. So every node is allowed to do one update. Okay. After 3 cycles, this is a kind of visualization. You can see it's still messy. There's still things going weirdly. After 5 cycles, it looks better. After 15 cycles, it's pretty much a perfect torus, where each node is, the closest ones are exactly the ones that are closest to it. Up, down, left, and right. So it works pretty well. Nice pictures, too. You can analyze now. So the paper does some mathematical analysis of this. And again, you have to use some tricks. You have to use some tricks. So I expect you to at least understand intuitively what these are, okay, these tricks. I'm not going to do the full analysis, but you have to get some understanding. First of all, the algorithm runs in two phases. Rapid convergence followed by endgame. That means when everything is very bad in the beginning, then it's easy to improve things. But once you get very close to a perfect torus, there's only a few mistakes left. So the random algorithm doesn't work so well anymore. You have to somehow figure out what are the mistakes and fix those. So at the very end, you have to change how the algorithm works, okay, to make it really go well. So that's why the algorithm has a rapid convergence phase, and at the end, you change it to make endgame, okay? Okay? And to analyze it, we can make some kind of approximation. After one cycle, you pick the best C out of 2C. If I have 100 vector, you pick the best 100 nodes out of 200 from the 2 nodes. But after I cycles, each time you're doubling, it's the closest C out of 2 to the I times C, as long as 2 to the I times C is smaller than the overall size, because then you start having sharing. So this is an approximate model that works as long as the number of cycles is small. Okay? And now they make an analysis of where the errors are coming from. Okay? First of all, it's random. This whole thing is random. Some nodes might converge very fast. Some nodes might converge slowly because of random choice. Some nodes very quickly might be perfect torus nodes. Or some nodes, maybe they're not. They're very bad for a long time. So this is not good, because the perfect nodes, so that's good, but the bad nodes will make the good nodes, the bad nodes, the good nodes will not really help the bad nodes, okay? So the best way is that they all converge at the same rate. That means they all get better at the same rate. So this is one thing you try to fix. You try to make sure they're converging at the same rate. So you do some tricks for that. Also, you have some other things. When nodes exchange views, again because of randomness, each of the vector is like a distribution, probability distribution. And again, it's better if they're the same distribution again. So this is kind of related. They have to converge at the same rate, and they have to be the same convergence. So basically, all the nodes have to go together kind of at the same rate to go to the torus. If some nodes are going faster than the others, then it hurts the algorithm. The slower ones, it does not help the slower ones, that there's some faster ones. But if the faster ones slow down, then they can actually help improve the slower ones, okay? So you want to make them all converge at the same rate. So that's kind of an idea. And then there's some analysis that was done here, okay? This is very, very, very vague, okay? So let's say we have some kind of topologies. So here it's a ring. So this is a node A. In a ring it has 2 neighbors, right? In a torus it has 4 neighbors. Binary tree, this is binary tree. It depends where you are. The root has 2 neighbors. The leaves have 1 neighbor, and the middle internal nodes have 3 neighbors. Okay? So these are kind of like numbers. That means for a torus, you actually have 4 ways of being closest to A. Whereas for a line, you only have 2 ways of being closest. Okay? So here it's extremely approximate. PAB is the probability that B is present in the view of A after cycle I. Okay? So B would be one of these nodes. Okay, one of the nodes, like for a torus, it'd be one of these. What is the probability that it's in the view of A after cycle I? Well, in the very beginning, it's C over n minus 1. if I have 100 vectors, but the size of the system is 1,000,000, then this is almost like 1,000,000, huh? Then there's a chance only 1 out of 10,000 that it's going to be right, huh? Okay? And now if I go from 1 to the next cycle, if I go from cycle I minus 1 to I multiply this by 2, okay? Okay? But this only if I'm within this C, in fact. Huh? So basically, but we can assume that that's mostly going to be the case. So PA after I cycle, it's 2 to the I times 0. But this only works, of course, when the total 2 to the I times C is much less than the size, okay? So that gives you some kind of an approximate analysis. It's very, very rough, huh? So here is the convergence factor. I told you it was 2, huh? I go C, 2C, and I pick the best. So in fact, I'm improving it by a factor of 2. Well, in the low number of cycles, it's close to 2. But as the number of cycles increases, it goes down, of course, because now we get close to the size of the network, huh? So we have sharing. So the 2 to the I times C doesn't work anymore because many of those are going to be the same node, huh? So it kind of goes down, but the edge is sort of at 2. So this kind of confirms that the analysis is reasonable, huh? The analysis says 2 and then 0, but in the real life it kind of goes like this, okay? So that's kind of the analysis they did to show why it works, and also the end game. So they do some tricks. The problem of the end is that you have almost perfect torus, okay? But there's a couple of nodes that are wrong. There's a couple of links that are like errors, little mistakes, but most of it is perfect. So if you do the random algorithm, most of your work is going to be wasted because you're just going to be rehashing all the perfection. Perfection will stay perfect, but you will never really get to the imperfect nodes. So somehow you have to focus on those imperfect ones, okay? So they made two optimizations. How do they work? How do they work? Why do they work? They work because they measured it and it works, okay? It's not so simple to analyze. So balancing, so this is during the rapid, so you have the rapid convergence and the end game, remember, huh? So in the rapid convergence, you want the nodes to converge at the same rate, okay? But maybe two nodes talk to a third node and they do their peer sharing with that one. Here, maybe you have this. I have P1 and P2, and they both pick P3. And P1 gets updated, P2 gets updated, but P3 gets updated twice. That means this one will converge faster. You see that? Because it does twice as, it now is able to look at much more nodes, converges faster. So this, we don't want this, okay? So a receiving node will refuse contact if there are too many. P3 will refuse contact from P2 if it already has contact from P1. You see that? Because otherwise it will converge faster because it's getting more information, okay? That means the sending node has to search for a willing receiving node. That means the sending node might say, I want to go to you, and the node says, no. Okay, I'll try you. No, no. And eventually it finds one, okay? So it has to actually search for a willing receiving node. That makes the algorithm more complicated, huh? But it balances out. Okay, and then the end game, you get rid of this random selection, okay? If you do random selection, the problem is that there's mistakes. But if you do random selection, you're not going to go on to those mistakes, okay? So you're not going to do random selection. You're going to pick one that's somehow close. You're going to do routing. You're going to follow. And that means if there's a mistake, you will actually make that mistake, okay? You want to increase the chance of hopping over the mistakes. you will actually do routing. Select one that's close on the topology, okay? So you will change how you pick nodes. If you do random, you're just going to be rehashing perfection, and that's not good. Huh? And then they did some measurements. It's actually very interesting to see how it works. Here you have cycles. So this one, the best one, is where you have optimal endgame. Okay, that means balancing and endgame. Notice, so these are the number of wrong nodes, huh? Yeah, there's a number of mistake problems. Notice it goes down, 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 and then it stays at 1 for a while. You see, that's interesting, huh? It takes a while to get rid of that last one. Boom. And here, this one, the dashed one, is no balancing. No, this one is no endgame. It's just balancing. No endgame, but notice at the end, getting rid of nodes is a lot harder and harder. Huh? Here you see it like steps down. It has to go, it goes here, and then it goes down, it goes down, it goes down. Eventually it goes and removes the last one. And if you do if you do only endgame from the beginning, then at the end you have all these steps going down. It's interesting, huh? Getting rid of the very last mistakes is hard, huh? In this algorithm. But it works, they did it. So you see they actually figured out how to make it work. Huh? And the worst one is if you do no balancing and no endgame, and then it's really, really slow. Okay? So it works, but you have to be smart, you see? You have this notion of endgame that you have to use. Huh? Oh, I'm way over time now, am I not? I am, huh? Well, let me just do one more minute and then we're done. Okay? So T-man is general, scales well, gossip framework, rapid convergence, endgame. You need to do optimizations, and systems really use this. So gossip works, but sometimes you have to be clever. That's like takeaway, yeah? Okay, let me stop there.